Course 3, Investigation 5. In this investigation, we are graphing transformations. We've done this in a previous lesson, so this really is just going a little bit deeper, especially into rotations and how to do those. But we'll also be looking at translations, reflections, and dilations. So I actually would like to do this warm-up first. So use coordinate notation to describe each transformation. So if I am doing 3 units to the left and 2 units down, I would consider this a translation because I'm sliding it. If I were to take a figure and push it and pull it and slide it, it's a translation. So when I take my original XY coordinates and change them into 3 units to the left and 2 units down, I would say that 3 units to the left is based on my XY coordinate. And going to the left is going into the negative, so I would be doing x minus 3. 2 units down, up and down is working with y coordinates, and going down would be like going negative, so y minus 2 would describe it. So that any coordinate that I am given, let's say I am given a coordinate point like 3, negative 2. And if I were to go 3 units to the left and 2 units down, I would be saying, well, that's my original, and now I need to do that x coordinate 3 minus 3, and my y coordinate negative 2, and I'm subtracting 2. So I would end up with a coordinate point of 0, negative 4. That would be my new coordinate point after the translation. So similarly, I could do 2 units to the right and 15 units down by saying xy moves to x, and then that 2 units to the right is like plus 2, and 15 units down is like y minus 15. So if I were to take a point like 3, negative 2, I'll just do the same one, I would be doing 3 plus 2, working with this, and then that y, so negative 2 and minus 15. So I would get a new coordinate point of 5, negative 17. That would be my new point after the translation. Okay. Now, we also need to be able to identify which transformation we have based on the rules. So I can kind of relate what I just wrote in 1 and 2 to this number 3 right here. This is saying that I would be going 2 to the right and 3 units down. So this would be considered a translation. Going back to number 1, 2x and 2y, each one of those I am multiplying by 2. This is getting bigger, so this is a dilation. If I have x, y, and I just make the x negative, this is actually considered a reflection. And based on which one is negative, in this case x is negative, so this is actually reflection over the y-axis. If you can consider it, it's like flipping over that y-axis. If my x's were in the positive region, I flip it over the y-axis and now it's in the negative region. And so each of my x coordinates is negative. All right, last one is number 4. xy goes to y negative x. Well, when you see those x and y flipped in their places, you can automatically assume that it's a rotation. Now, which type of rotation is a little bit harder to remember. But how I like to remember it is, well, if I have just one of them being negative and they flipped spots, well, then I would consider that a 90-degree rotation. And based on which one of them is negative, either the first one or the second one, I can consider this clockwise or counterclockwise. Well, if you consider this kind of like a clock, here's my middle and here's my 12 o'clock up here. If I go this way clockwise and I hit that one and it's negative, then it's a clockwise rotation. I'll talk more about that little trick in just a second. But if this were a clockwise or a counterclockwise rotation, and I went counterclockwise and hit y being negative, then this would be a counterclockwise rotation. I'll talk about that more in a little bit. Now, the other part of this is really just being able to take a figure and being able to translate it. So let's dig into the investigation. It says, recall that transformations are operations on a geometric figure that alter its position or size. In the investigation, we'll graph different transformations on a coordinate plane. This is definitely one where you need to be using graph paper. First one we're going to look at is a reflection. You can see kind of an overview of all four right there. But a reflection occurs across a line. Typically we use x-axis and y-axis, but we can actually reflect over any line. Below we show the reflection of triangle ABC across the y-axis. If we position a vertical mirror on the line, so right here on the y-axis, the reflection of triangle ABC would appear to be on the other side of the y-axis and the same distance from the y-axis. For example, this A is 2 units, 1, 2, from the y-axis, and this A prime is 2 units away from the y-axis. That's not just by chance, that is definitely by design. Each one of these points and the corresponding ones are the same units away from that line of reflection. So our triangle ABC would appear to be on the other side of the y-axis and the same distance from the y-axis as triangle A prime, B prime, C prime. Segment between the corresponding points of a figure and its reflection is perpendicular to the line of reflection. So if we were to fold a graph along the line of reflection, the figures would align exactly. The part about the perpendicular is saying if I draw a line from this C to the line of reflection, it would be a perpendicular line, 90 degrees. And same from the C prime to our line of reflection, 90 degrees. Same with each one of my points. So, on a coordinate plane, draw ABC. If A were at -2, 6, here's my A. B is at -5, 2. And C is at -2, 2. So here is my original figure that I am going to be reflecting. We want to draw a reflection of triangle ABC across the x-axis this time. Label the coordinates of the vertices. So instead of the y-axis like we saw above, we want across the x-axis. Now there's a couple ways that we can do this. If you can visually see it, then we can use the distance to that line of reflection to reflect it back the other way. So for example, this B coordinate. It is 2 units away from that line of reflection, going down. Well, if I continue on the other side of that line of reflection 2 units, I find my coordinate point for B prime. So I could do the same for, let's say, A. That's 1, 2, 3, 4, 5, 6 units away from my line of reflection. So I could go 6 units on the other side to find the new coordinate for A prime. Okay, let me just erase it so we have a little bit better visual of all of this. The other way though, especially if you have the coordinate points, is by saying, if I do an x-axis reflection, that means that it's actually staying the same x values, but all of my y values are at the opposite of my original. So what we are saying is, with a rule, I'm saying x comma y becomes x comma -y. All of my y coordinates for my x-axis reflection become negative. So if I were to take this c value of -2, 2, it would become c prime at the same x value, so -2, but now my y value becomes negative at -2. And so I get this point right here, which is exactly where we wanted it to be. So we can use our rule as well for this reflection. Now, just so that we have it down, our y-axis reflection is similar, but instead of keeping my x value the same, I keep my y value the same and make my x negative. So -x comma y. Okay, back to those problems. Describe how the coordinates of the reflection across the x-axis compare. Well, that's exactly this right here, is that my x coordinates are the same, but my y coordinates are now negative. Number 3, on the same coordinate plane as problem number 1, draw a vertical line through the x-axis at x equals 1. So vertical line here, I'll draw it with a dashed line at x equals 1, right there. The line should be parallel to the y-axis, check. Then graph the reflection of A prime, B prime, C prime across that line. Name the reflection A double prime, C double prime, B double prime. Now what this is saying is from this A prime, B prime, C prime, I want to be the same amount of units away from this line of reflection, but on the other side. So it's like flipping across an axis, but we don't have some of these fancy formulas to use. We just have to use the distance. So for example, A prime is 1, 2, 3 units away from that line of reflection. So I want to be 1, 2, 3 units in the other direction. So here's my A double prime. Here's C double prime. So, oops, 1, 2, 3 units away. So still going across 1, 2, 3 units away. Notice that my y coordinates aren't changing. It's just the distance of x. So this is my C double prime. B double prime, we go 1, 2, 3, 4, 5, 6 units. So 1, 2, 3, 4, 5, 6 units. And here is B double prime. Oops, sorry, that little one missed. All right, here is my triangle, and now it has been reflected across that line of symmetry. Okay? All right. So to practice reflection over a little bit more, what we can say is if I had this right here, I'm just kind of pointing out these rules again. Over the y-axis, the x becomes negative. And you can check this. If these are my original, you can see that all of my x coordinates have become their opposite. If you have a question as far as, well, what if it already starts out as negative? Like if I had -2, 3. Well, we would use its opposite. D prime would be -2, which is a +2, the opposite of -2, 3. And if we have our x-axis reflection, our y becomes negative. Notice how all of these y's are negative now because they started out positive. All right, now a rotation, a little bit harder than reflection, but we also do have rules about this as well. So a positive rotation turns a figure counterclockwise. Remember, counterclockwise is the opposite of the movement of a clock, so kind of to the left. Here we show a 90-degree rotation about point B. We can do it around points or the origin, doesn't really matter. The origin is, though, easier and what we're mostly going to be doing. So point B is the point of rotation, and it's fixed, so the point stays where it is. And we spin around it. If we trace out the point of any other point during this rotation, so let's say from A to A prime, it's a 90-degree rotation. All right, now I can't really show this necessarily on here very well, but if you would like to, I would say stop the video and use a really thin piece of paper or a transparency film or something that you can use for tracing. Because what you can do is trace out this figure right here and rotate your paper. You can do it counterclockwise or you can do it clockwise and see what happens after a 90-degree rotation. I can't show you this on this video, but you can see from this original position, if I were to do a 90-degree rotation counterclockwise, I would now be left with a figure right here, A prime, B prime, C prime. This is a new figure, 90 degrees rotated counterclockwise. We could also take this and do 180 degrees. Let's say we went from my original triangle right here, 180 degrees. We would actually be left with a triangle that looks like this, with A, B, and C. All right, now we actually have some really good rules to do this rotation, and it really does help to do the transparency paper, so as much as you can, please try and do that activity. But with rotations, to be honest, it's very difficult to try to do just by sight. Using the formulas really helps. So when we do a rotation, the thing to remember is when it's 90 degrees, we're going to flip the x and y coordinates. So for a clockwise rotation, we have xy becoming y negative x. So they swapped positions, and my second part of the coordinate has become negative. For counterclockwise, we still flip them, but now my first part of the coordinate is its opposite. How I was trying to explain this earlier is think about a clock, okay? And if my coordinate was part of that clock, let's say we'll just say our y and our negative x. If I were to go clockwise around this, then I know if this first coordinate that I hit, this first part of the coordinate that I hit while going clockwise around, if that is negative, then it must have been a clockwise rotation. But let's say I were to flip it and now this y is negative. If I were to go counterclockwise here, I hit that y as negative. It is a counterclockwise rotation. What this helps with is, say we figured out a rule and or we needed to remember the rule for clockwise and counterclockwise. And if you remember that we flip the coordinates and you say, well, I need a clockwise rotation. If I want a clockwise rotation, I must be going this way, so it must be my x that becomes negative. Or if you need a counterclockwise rotation, then my y must become negative, since that's what I would hit first when doing counterclockwise. Hopefully that helps you. I know it helps me to remember it. But a 180-degree rotation still works with those negatives, but now they're back in the same spots. We've flopped them again. So let's say, I'll show this for example, if I have xy being at 0 degrees rotated. Let's say I did a 90-degree clockwise rotation. That means that I flopped them, so I had x and y, and I made that x negative. Now maybe I do another 90-degree clockwise rotation, okay, which means I've done a full 180. That means that I flopped them again, so I have negative x comma y, and I made this second one negative. Well, this in total equals 180-degree rotation. Doesn't matter if it's clockwise or counterclockwise, it will end up in the same spot. But we have come up with a 180-degree rotation by using negative x comma negative y, because we flopped them so much, but they've become their opposite in the process. So with 180-degree turns, we are going to just make x negative and y negative in those same positions. All right, now a little bit more about this. So if I were to use this triangle here in order to do one of these rotations, let's say a 90-degree counterclockwise, you'll see it abbreviated like that sometimes, and a 180-degree rotation. So I'm actually going to use the coordinates of these. It makes it a lot easier. So A is at, let's see, 0, 8. B is at 4, 2, and C is at 0, 2. If I want to do this 90-degree counterclockwise rotation, I need to change all of these so that I have them flopped, so y and x, and the first one is now its opposite. So I flop them here. I get 8, 0, and the first one's going to be negative. I flop the 4 and the 2, and the first one's going to become negative. I flop the 0 and the 2, and the first one's going to be negative. So my 90-degree counterclockwise rotation going this way is going to be at negative 8, 0. So right here is my A prime. Negative 2, 4 is going to be my B prime, and C prime is at negative 2, 0. So right here. A lot easier to do it that way than trying to do it just by sight. Okay, but if we do look at if my origin is my point of rotation, which it is, of course, I can see that each one of these from the original, let's say C to its new point, so down to the origin and then over to that C prime, it's a 90-degree angle. Or from B to B prime, that is a 90-degree angle. Each one of those, it's with its rotation, will give us a 90-degree sweep. With the 180-degree, I'm going to now have coordinates that are just their opposite numbers. So 0, negative 8, and negative 4, negative 2. and then 0, -2. So that when I go from my original 180 degrees, I now have A double prime down here, and I have B double prime right here, and C double prime right here. And here is my 180 degree rotation from the original. Okay, so that's our rotations. It really is easiest to do it based on the rules rather than trying to just visualize where it's going to end up. And now we actually end with our probably easiest two, translation and dilation. So translation slides our figure a direction without flipping or turning. We show a translation of 6, 1, or like I like to describe it, x plus 6 and y plus 1. So that our first one describes the horizontal shift, left or right, and our second part describes up and down, our vertical shift. We can actually see this by just counting the points as well. So let me get a little bit closer here. Let's say we're going from A to A prime. If I go horizontally, 1, 2, 3, 4, 5, 6, and then up 1, I get to A prime. Or maybe with my B values. I go 1, 2, 3, 4, 5, 6. Sorry, I missed a little bit there. And then up 1, we get to my B prime. So what we're going to do with 6 and 7, we're going to translate a little bit. So draw the triangle ABC as illustrated on a coordinate plane, then draw its image translated 7 units to the right, so x plus 7, and 8 units down. So we are going to do then y minus 8. You can do this by actually counting out all of those squares, or you can do it by actually finding the coordinates and plotting those. So let's just draw ABC again. And let's see, B is at -5, 2, and A is at 2, 6. All right. Here's my original, and now I need to move it 7 units to the right, 8 units down. So I'm going to show you both ways. Let's say if I take A and count out how to go from one to the other. Then I would be counting out from A horizontally. 1, 2, 3, 4, 5, 6, 7. And then I'm going to go down 8 from here. 1, 2, 3, 4, 5, 6, 7, 8. And here is my new A value at A prime. Now you can absolutely do that, but when you get into really big numbers, it's going to be tough. So what if I took the values, the coordinates for B, and changed them to B prime? Well, B right now is at -5, 2. If I were to use this formula up here, I would be taking -5 and adding 7, and taking 2 and subtracting 8, so that I get a coordinate point for B prime at 2, -6. Well, 2, -6 is right here. That's at least looking good for the value of my triangle. There's my B prime. All right, and then C prime, I'll do the same with the formula. C is at -2, 2, and when I use the formula, I get -2 plus 7 and 2 minus 8. So I get C prime at 5, -6. 5, and we are at -6. And here's my A value up here. And that triangle looks just like the same up there, but translated to the right 7 and down 8. Now 7 says, if ABC is translated so that the image of point A at A prime, A double prime, is located at the origin, so we want A double prime to be at the origin, then what would be the coordinates of point B prime and C prime? Well, let's see what happened with my original A value to get it to that point. So horizontally, I must have moved 2 to the right, so I must have done x plus 2. And then to get to that A prime, I need to go 1, 2, 3, 4, 5, 6 units down, so y minus 6. So to do the same for B and C, I would be taking B at -5, 2, and translating it using the formula above to get b prime at, well, -5 plus 2 is -3. 2 minus 6 is -4. So my b double prime is at -3, -4. So right here. Same with c. I had at -2, 2. So my c double prime must be at 0, comma, -4. Right here. So there is my new triangle with that translation. All right, now we're looking at dilations. Recall that reflections, rotations, and translations are called isometries, meaning same measures, or congruence transformations, because the original figure and its image are congruent. What this is saying is that reflections, rotations, and translations, all they do is move and flip and slide things. They don't actually change the side or the dimensions. A dilation is a transformation in which the figure grows larger, while a contraction is a transformation that makes it smaller. A lot of times you'll hear that a dilation is called an enlargement when it gets bigger and a contraction when it gets smaller. So dilations and contractions are similarity transformations, not congruence transformations, because the original figure and its image are similar but not exactly the same. So those corresponding lengths are proportional. Dilations of geometric figures occur at a fixed point called the center of dilation. On a coordinate plane, the center of dilation will be any point, but for this course, we will just be using the origin as our center of dilation. What that means is our figures are probably not going to actually be on the origin. It just means that our dilations are going to be based on that point, so that when I have my old coordinate with my new coordinate, it forms a line with those 3 points. You can see that with each one of these. So what we're going to do here is graph one of these and then make it its dilation, whether that's an enlargement or a contraction. But remember how we do this. Recall that to graph a dilation on a coordinate plane, we prescribe a scale factor, such as 2. If the center of dilation is origin, we can just multiply it by the coordinates. So for example, if I have a scale factor of 3 with a vertex at 1, 3, I could make it its new coordinate by just multiplying each of the parts of the coordinate by 3. So I could do 1 times 3 and 3 times 3, which gives me my new coordinate at 3, 9. So let's try this with A, B, and C. Okay, so if A is at 6, 4, and I want a scale factor of 1/2, I am going to do A prime at 6 times 1/2, 4 times 1/2. So A prime must be at 3, 2. B prime, I'm going to take half of 6 and -2 and get it at 3, -1. C prime is going to be at -1, -1, half of both of those, and D prime is going to be at -1, 2. So that when we actually plot each of these, you will see that it's very similar looking, just a little bit smaller. So let's go ahead and graph those. All right, so A was at 6, 4. B was at 6, -2. C was at -2, 2. And D must have been here at -2, 4. Which means when we use our dilation now, we should see this figure just a little bit smaller inside of this big one. Okay, it's not always going to be inside, but this one does actually end up inside. So we take half of the coordinates. We have 3, 2 as my first one, so A prime. B is going to be at 3, -1, so B prime right there. C prime is at -1, 1, and D prime is here at 2, -1, or -1, 2. So here is my smaller version that is similar to the big one, but not exactly the same, since this is a similarity transformation, not a congruence transformation. All right, so interesting questions here. What fraction of the dimensions of A, B, C, D are the dimensions of A prime, B prime, C prime, D prime? And what's the fraction of the perimeter to the perimeter? So if we look at this, the side lengths of the big one, our original one, are, let's see, 1, 2, 3, 4, 5, 6, 7, 8 by 6. Our small one is half of that, 4 and 3. So the fraction from side lengths to side lengths is 1/2, just like our scale factor. Wonder if the perimeter is going to be the same. We have 8 and 6, 8 and 6. When you add all that up, you get 28 for the big one. So perimeter of 28. And perimeter for the prime one is going to be 4 and 3, 4 and 3, so 14. It ends up being the same. Perimeter to perimeter, I'll put a little prime with each of these, is 1/2. Well, number 10 asks us actually about the areas. Is this fraction going to be the same? Well, let's see. The area of the big one is 48. The area of the small one, so area prime, is 4 times 3 of 12. So it's not actually half. A to A prime, area to the next area, is actually 1/4 of the size. There's actually a reason behind this, which we look at in detail in another lesson, but it actually comes from the fact that side lengths and the perimeter are one-dimensional, while area is two-dimensional. This 1/4 actually comes from 1/2, and since we're in two dimensionals, I am squaring it. 1/2 squared is 1/4. Very interesting relationship there. So just to review over what all we've done in this investigation, remember that translations, rotations, and reflections are all congruent. We are just taking that figure, putting it in a different location. So our enlargements and our contractions are similar, but not congruent. All right, now I'll leave these for you to try. The only change that I will make is doing the counterclockwise rotation around the origin. Okay, makes it a little bit easier and more like what we actually practiced in this lesson. But go ahead and try those out for yourself now that you've seen all of these in this investigation. All right, I hope this video helps you out with your homework and for studying.